Good morning, everybody. So last time we started implementing SARSA, and then I left a bit of time to implement on your own Q-learning. I don't know if you all have managed to complete that implementation, but just in case some of you haven't, I'm going to implement it right now in front of you, so those who haven't can catch up. And then we're going to play a bit with Q-learning. I think that's going to take at most 1 hour. And then the rest of the lecture, we're going to start talking about how we can generalize these reinforcement learning algorithms from discrete spaces to continuous spaces, which is much more useful for robotics applications. So this is the template code for implementing Q-learning. This is like empty function, as usual, filled with comments. So I'm just gonna go ahead and implement it using the comments we have here. So making a copy of the Q table, this is just for keeping track of convergence. We can do it or not, doesn't matter, but since it's there, we're gonna do it. Then for every episode, so I'm gonna do a for loop over the episodes. I'm gonna reset the state of the system with the reset function. And then I'm going to simulate it for t in range max episode length. Okay. So for every step, I need to choose a control action. Here we can use anything, because in Q-learning, the only requirement we have for the control actions that we choose is that they are exploratory. So any policy that is exploratory, so that has some stochasticity embedded, would be fine. We're going to stick to epsilon greedy because that can be exploratory. And actually, we already have the implementation of the epsilon greedy here in SARSA, so I'm just going to copy paste it from here. So EPS is called in this script exploration prob. Should have changed that to be consistent with the other, but it's just a different name for the same, exactly the same thing. And then I can take a step. Every time I take a step, I get the next state and the cost. And then I can compute the reference Q value at state X. So Q target is going to be equal to the current cost plus the discount, which is gamma, times, and here I have to evaluate Q at the next state. And for the next control input, here I'm not going to use the real control input that I'm going to choose, but here I'm going to take the best control input. So I'm going to minimize with respect to the control inputs. And using these Q targets, I can update my Q table. The learning rate is called learning rate. So learning rate times Q target minus Q X U. Then I should keep track of the cost to go. So let me do it like that. Cost to go plus equal gamma to the power of t times the current cost. So I can save it at the end of each episode. And I adjust to update epsilon. So epsilon here is called exploration probability. And I set it to an exponential minus exploration decreasing decay times the episode number. And then I saturate to the lower bound. Okay, so the algorithm is finished. Now I just have to do the usual prints and plots. So if episode percentage, what's the name, and print equal to 0, then I can, as the comment suggests, I can use this function here to compute the value function. Compute v pi from q and q, which allows me to print some interesting information like episode number, d, and then I can print like the mean value. And I don't remember exactly what we were printing in SARSA. Let's try to print the same stuff so we get the same information. Let me just copy these lines. Okay, so I print the episode number, the value of epsilon, the average of the value function, and the average of the cost to go. And then if a plot is true, I also do a plot of the value table. I think if I remember correctly, okay, let's give it a try. I think there's gonna be a mistake here, but let's see. So this was the last run of no, this wasn't, sorry. It was still Q-learning. Let me make sure that I'm using the correct solution. So the one I just implemented. Okay. So Python x5 qlearning.py. I'm running it with the default value for the parameters. And indeed, there is a mistake. Let's see. Okay, it's complaining about the use of the max function. I think I should just use the default max, not the numpy max, because the numpy max wants a list of values instead of giving it just two values. Okay, now it worked. And you can see that epsilon saturates at 50%. So that's very different from what we were doing with SARSA, because in SARSA, we have the requirement of making epsilon go to 0 to ensure convergence. In Q-learning, we don't have that requirement. Actually, we have kind of the opposite requirement. We need epsilon to remain quite large. Yeah.
Sorry, I was not clear about that. I was clear what epsilon is.
It's the exploration probability. When you do an epsilon greedy policy with probability epsilon, you take a random action. So if epsilon is large, it means that often you take random actions, which makes you explore a lot. So here we are leaving, I mean, we start as usual with epsilon 100%, and we make it decrease. But in SARSA, we need epsilon to decrease to very small values. So in last time, we were making it go like to 0.1%. Here we don't have that requirement. So epsilon can remain large. Actually, it could remain even at 100% the whole time, and it should still work. It's not working, apparently. So I must have made a mistake. Let's see if at least it executes without errors, because I think there's going to be a mismatch in the size at the end. Yeah, indeed. So there is a mismatch in the size, because here I was expecting the episode numbers to start from 1. So yeah, just do that to fix the mistake. And there is a mistake here. I see it. Do you see it as well? Yeah, I forgot to update the state. So here I should do x equal x next. That was the problem, I think. Let me try to run again. Yeah, it was the problem, because you can see now that the value function is decreasing. Before it wasn't. But you can notice that the cost to go is not decreasing much. So the value table looks pretty good. I mean, we have some spots here where clearly learning has not converged, so you have a much higher value. But in most of the state space, you have a good value. This is a policy, which is very much harder to read than the value. But in case you want to take a look, that's it. And now what we do is that from the value that we get out of Q-learning, we compute the greedy policy, and then we evaluate the greedy policy. And that does not necessarily give you the same value that you started from. Stopped working? Okay, we're back. And so this is the value of the greedy policy. And indeed, we can see that the average is slightly different. So the average value computed by Q-learning was minus 4.5. And instead, the average value of the greedy policy is minus 4.6. So it's a bit better, actually. And now instead we compute the optimal value function using policy iteration, just to see what is really the best value. And we can see that it's pretty close. It's minus 4.69. So we are very close to global optimality using Q-learning in 5,000 iterations. But despite having like almost an optimal policy, we can see that the cost to go during training is very bad. It's minus 0.3. If you compare it to the average value, which is minus 4.6, this is super high as a cost. Why do we have a high cost during training? Yeah, it's because we are taking random actions 50% of the time. So of course, we cannot perform good.
Wasn't also because of SARS that we use the epsilon transitions.
We use epsilon going to 0. Here we use epsilon going to 50%. So in SARSA, it's true that you start in the same way by being very exploratory, but after a little while, you are quite greedy. And so at the end, I mean, we can run SARS again to see Python X4 SARSA. You will see that with SARSA, not only the value, but also the cost to go decreases. You can see that they are quite aligned, actually. They give very similar values. So this is the cost to go with SARSA, and you can see that we at the end we are at minus 1.4. With Q-learning, we were at minus 0.3. We were here. And that's because epsilon doesn't go to 0. I mean, you can make it go to 0. We can try actually. But for how we set parameters, it doesn't go to 0. It remains at 50%. And so the cost to go of the episodes cannot really decrease much because you're mostly taking random actions. But despite mostly taking random actions, you actually learn a policy that is better than the one that we learn with SARSA. Because we can see with SARSA, the value of the policy that we get is minus 3.2. With Q-learning, it was minus 4.6. So it's much, much better. So with Q-learning, we are accelerating the learning. Because the number of episodes I'm doing with SARSA and Q-learning now are the same. It's 5,000 episodes, same length, same discount factor, same learning rate. Everything is the same. So of course, you can also make epsilon go to 0 in Q-learning. Well, not really to 0, but you can make it go like much lower. For instance, we could make it go to 1% instead of 50% if we also care about the performance during training. And you can see that now, since epsilon is getting small, also the mean cost to go is decreasing. So the policy that we got is almost as good as the one we had before. It's a bit worse, but not much. Before we were at minus 4.6, now we are minus 4.5. But the advantage now is that during training, we have exploited more. We have been more greedy towards the end, especially. And so we can see that also the cost to go of the episodes now is going down.
How low is like the lowest possible?
It's minus 4.69. That's the best average value. So being at minus 4.5, it's pretty good. We're very close to the best we can do. If we kept training for longer, we would reach it eventually. It just take longer. So it's a trade-off between how fast you want to learn the optimal policy and how much do you care about performance during training. So if you're training in simulation, as we are right now, typically you don't care about performance during training. It's just a simulation. You're just trying to learn the best policy for then like applying that policy on the real system. If instead you're training directly on hardware by collecting data, then it's the opposite. You typically also care about performance during training, and so you maybe don't want to explore so much as we were doing before. Anyway, in general, we can see that Q-learning is really an improvement over SARSA because it allows you to learn faster, and then you can decide how much you care about performance during training by adapting your behavior policy to be more or less greedy and exploratory. Okay. Any question, doubt? That's all I wanted to show you on Q-learning. I hope you have now a good understanding of the differences between Q-learning and SARSA. I mean, in practice, how they behave differently.
So if Q-learning seems like you would like if just better, why we have also SARS?
You have SARSA because it came earlier, and then Q-learning came later as an improvement over it.
But Q-learning just better, or there are some cases where I want to use SARS.
So if you care about performance during training, which is not the case most of the time because we are doing most of the training in simulation. But if you are in that case, then SARSA might be a better choice because SARSA is basically accounting for the epsilon probability of taking random actions in the evaluation. And so it's behaving in a way that is a bit more conservative. Like if you have a risk of incurring into a high penalty when you take a random action in certain states, like you have certain states that are very close to a dangerous state where you're gonna have to pay a high cost if you go there. SARSA is gonna avoid visiting those states often because in the Q function, it accounts for the probability of taking random actions. Q-learning instead does not do that. So Q-learning assumes that in the future, the policy is always going to be greedy. And so it's never going to explore and take random actions. Even if in practice you are taking random actions, actually, you are taking random actions more often in Q-learning than in SARSA usually. And so it might take risks, basically. It might visit states from which taking a random action leads to very high costs. because it does not assume that in the future you're going to take random actions. So if you want to have an algorithm that is more cautious and aware that there's going to be exploration, SARSA should be your choice. But that applies only if you really care about the cost of during training, which is meaningful if you're training directly on hardware. But for most robotic system, training directly on hardware is very hard because we have like high dimensional state spaces. So you need lots of data and you have a high cost of failure on hardware because you might break the robot. That's why training in simulation is much more common than training directly on hardware. Okay, we can now switch to the lesson on extending reinforcement learning to continuous action spaces. Well, not action spaces, but to continuous spaces in general. Assuming this works. So far, we have only seen reinforcement learning in the tabular setting. So you have a discrete state space, a discrete action space. Everything is discrete. So we can represent a policy with just a vector. A value function is again just a vector. A Q function is a matrix. And that makes everything very nice and easy to implement and also easy to analyze. We have convergence guarantees for these algorithms in the tabular setting. But the problem is that if you want to go beyond like simple type problems, like you want to go to real problems, even remaining in the discrete setting, like you want to play board games like backgammon or Go, well, you're going to have a very large number of states, like 10 to the power of 20 for backgammon or 10 to the power of 170 for Go. So good luck storing a vector with that many entries for the policy and the same for the value. There's no way you can do that on a computer. And if you go to robots, then things are even worse because robots have a continuous state space. You can try to discretize it, of course, but we have already discussed that scales very badly. Like if you have a robot manipulator, basic one with 6 joints, for each joint you discretize with just 10 values, which is a super rough discretization. Then you're going to have 10 to the power of 12 states. So that's a bit too large to work with. And that's a very bad discretization. If you want to have a good discretization, like 100 values, and of course it's even worse. It's 100 to the power of 12 states. So it doesn't scale at all. We cannot hope to keep going with these tabular methods. So the way that reinforcement learning has been scaled to solve these real world problems is by introducing function approximation techniques. And at first they were only used for representing the value or the action value function. So instead of storing the action value function as a vector, as a matrix, you store it as a function approximator, which is parametric. So for instance, here the parameters are represented by W. So these are going to be typically the weights of a neural network. That's why we call them W. And then by changing W, you're changing the function that this function approximator is representing. And you can try to make this function fit the real data that you collect on the system. And this scales much better because even if your state has a very high dimension, then what's going to matter for scalability is going to be the size of the parameter W. It's not the size of X. And you can hope that this function has some structure or some smoothness so that you can represent this very high dimensional function using a relatively small number of parameters W. And so this can scale to high dimensions. And in practice, that is really what happens, and that is why this can work. So when it comes to representing value or action value with function approximation, you have these three different schemes. Well, for representing a value, you just do it. There is not much to discuss here. So your function approximation takes as input the state X. It is parameterized by your parameters W, and it gives as output a scalar, a single scalar, which is the value associated to that input state. Very straightforward. For the action value, instead you have two options. You can either do basically the same, so you take as inputs both the state and the control, and you give as output a single scalar, which is the action value. Or if your actions are discrete, you can take as input only the state and give as outputs multiple values, one for each action, and each output is the value corresponding to the input state X and one specific action. So this works if you're in the hybrid setting where the state is continuous or very high dimensional anyway, but the action space is still discrete with a relatively small dimension. And this is interesting because there are, I mean, typically the control space is smaller than the state space. That's especially true in like video games, where the state space is typically the pixel space of the image of the game. So that's super high dimensional. But the control space is basically coming down to the buttons and the joystick directions. So that can be represented with very, very few values. And even for robots, very often the action space is much smaller than the state space. Like for a quadruped robot, for instance, the state space has 36 dimensions. The action space has 12 dimensions. So it's like 1/3 of the size of the state space. So this can happen, can be useful. So actually, I already talked about neural networks for function approximation, but in principle, you can use any function approximation. You don't have to be limited to neural networks. It's just that neural networks are the most popular ones nowadays. But back in the days, people were using all kinds of function approximation techniques, like linear combination of features was very popular because you were linear with respect to the parameters, and that allowed you to still give some convergence guarantees for these algorithms. Fourier bases can be used, polynomials, which are a very simple kind of function approximation technique, can be used as well. However, scaling to complex and continuous spaces is not just a matter of saying, okay, I'm going to replace my table with a function approximator. Because the problem here that we're dealing with is quite different from the classic setting in which function approximation techniques are used. So if you've taken any class on supervised learning, which is a most standard way of doing machine learning, you're gonna know that you have this assumption. It's called IID. It stands for independent, identically distributed. So you assume that all your data points are independent and they are sampled from the same distribution. Okay, that assumption is true if you're doing like classification of images. It's a very classic supervised learning problem. So you have a set of images and you want to recognize whether the image contains a cat or a dog. In that case, you typically have the IID assumptions holding. When you're doing reinforcement learning, that assumption does not hold anymore. Can you guess why? Especially the independence part.
Because at each time step, the next time step is dependent on the previous state.
Yeah, exactly. So your data points are going to be the transitions, the ones that we use also in Q-learning and SARSA. And the transitions that you have at time t is not independent of the transition you had at time t minus 1. Actually, they are very dependent because the state evolves continuously in a dynamical system. You don't just jump randomly from one state to another. And so this dependence between consecutive states breaks this assumption, which is going to make the learning part much harder here in reinforcement learning than it is in classic supervised learning. And also you have a second problem that you're trying to learn the value function, and that's going to be the value function associated to the policy that you're learning. But that policy is changing because you're improving the policy during the training of the algorithm. And so also the value function that you're trying to learn is changing. And so basically you're trying to fit a function that is changing while you're trying to fit it. So that's not classically what you do in supervised learning. So you have these two issues which make applying function approximation in RL much harder than it is in classic machine learning. And then we're going to discuss how these are fixed.
Are the value functions changing because it depends on the state?
No, it depends. Well, of course, it depends on the state. It's a function of the state,
Yeah.
but that's not a problem. Every function depends on its inputs.
Yeah.
That's standard.
It depends on the cost.
It depends on the policy. So the value that you're learning is not the optimal value. I mean, at convergence, hopefully you're going to learn the optimal value function, and that is fixed. But what you're learning during training is the value function of the current policy that you have.
Yes.
And that current policy is improving over time. We have just seen it in Q-learning. At the beginning, you perform poorly, and then little by little, you improve. So the value that you have is the value of the current policy. And that policy is changing. So the value function that you're learning is a different value at every episode, basically.
So I'm trying to approximate a function that is changing
over time.
in each
episode.
Yeah.
Yeah, basically every time you change the policy, you're also changing the value function,
which I'm trying to approximate.
Which you're trying to approximate. So you have like a moving target.
Yeah.
It's like shooting a moving target. It's much more difficult than shooting a stationary target.
Thank you.
So before we discuss how we can use these function approximation techniques in RL, let me give you like a very quick introduction on neural networks for those of you who haven't seen them, because we're going to use them later on. So you need to know a bit what they are, and especially the vocabulary. So neural networks are actually nothing more than parametric functions with a specific structure. They are structured in layer. This is typically how you represent a neural network with a graph. So you have an input layer, an output layer, and you might have one or more hidden layers. Well, typically you have more than one hidden layer, but in this simple picture, you just have one hidden layer. The size of the input layer is simply the size of your inputs of the function. So in our case, it's going to be the size of the state space. And the size of the output layer is the number of outputs of the function. For the hidden layer, instead, you can have whatever size you want. That's completely up to you. And you have to decide that when you create the neural network. Each layer is composed of neurons. So these little circles here, they are called neurons in the neural network jargon. And if your network is a fully connected network, which are the most common type, that's also the type we are going to use, then each neuron is connected to all the layers, to all the neurons of the next layer and to all the neurons of the previous layer. So you can see that here, this neuron here is connected to both neurons of the input layer and is connected, of course, to the only neuron of the output layer. So you have full connections between layers. Which means that this neuron here is going to receive as input both these values here. Each neuron outputs a nonlinear function of a linear combination of its inputs. And this is better described here in the next slide. So if we zoom in to a single neuron receives a number of inputs from the previous layer. In this case, it's 3 inputs. And the output of that neuron is computed, first of all, by taking a linear combination of the inputs with some values which are going to be the weights. Typically, you also have a weight which is a constant, and this weight is called bias. And then after you have taken a linear combination of the inputs, you go through a nonlinear function g, which is called the activation function. Very classic activation functions are the rectified linear unit, also called ReLU, which is simply the max between 0 and the input. So it's a function that's going to look like this. It's going to be 0 for negative input, and it's going to be like a straight line with unit derivative for positive. So this is a ReLU function. Or another very common one is a hyperbolic tangent, which is instead going to look like this. Or here it's converging to 1, and below it's converging to -1. And it's very important that the activation function is nonlinear, because what happens if you take a linear activation function? Well, it's not a constant because the weights are they're not going to be constant during the learning. You kind of change them. But if you take a linear function of a linear function, what do you get? A linear function. So if the activation functions are linear, then the whole network is just a linear function. And that makes no sense. I mean, if you just want to learn a linear function, you don't need neural networks. You just code it as a linear function, which is much, much easier to learn, actually. But we need to use nonlinear activation functions because typically we want our neural networks to approximate nonlinear functions. And so we need some nonlinearities inside the network. And it's quite surprising that even the ReLU, which looks like almost linear, right? I mean, it's linear before zero. It's actually a constant. It's linear after zero. But just the fact that you have this like piecewise linear function is enough to make the overall network actually very nonlinear. And it's actually proven that using just ReLU activation function, a neural network can approximate any nonlinear function to any degree of accuracy. And you just need one hidden layer to do that. But this hidden layer could have an arbitrarily large number of neurons. And this is why actually neural networks are called like universal function approximators, because there is this theory behind that guarantees that with a neural network you can approximate any nonlinear function as long as you have enough neurons in the network. So learning the parameters, so the weights of the neural network is the so-called training process. So when people talk about training a neural network, what they actually mean is finding the values of the weights of the network so that this network is a good approximation of some data. You can see the training as actually solving an unconstrained minimization problem, which looks like this, typically. So you're minimizing over W, which are the weights of all the neurons of the network. And your loss function is measuring the distance between the desired output of the network and the output of the network computed with the given weight and for the associated input. So you're basically given a list of input-output pairs, X, Y. So, and you would like your network to produce the output Y given the input X. So of course, if your network is able to make this error 0, it means that it's exactly predicting all the outputs given the inputs. In practice, it's not going to go to 0, this error, but if you typically manage to make it small, then you're going to have a good approximation of the function. Here, this summation is over all the samples that you have in your data sets that you're using for training. And typically in a classic supervised learning problem, this data set is fixed and it's given at the beginning of the training process. And so what you're going to do is that you're going to basically use all the data that you have at the beginning, and that's going to be all. In reinforcement learning, things are a bit more complicated because we typically need to train as we collect data. So we are not going to start with just a data set and we just have to learn this fixed data set, but we're going to start with some data, we're going to do a bit of learning, and then we're going to collect new data and we're going to improve learning, and everything is going to be much more interactive. So okay, just a bit of vocabulary. The function that you're minimizing during training is typically called the loss function. But that's exactly the same as the objective function or the cost function, which is typically how we call it in optimal control. or just in standard optimization.
I was wondering if you had that data set and you discover later that the data set was wrong. Is it hard to update it, the training model if there are some mistakes in it?
So the networks have this property of forgetting data that you don't use for training after a while. So typically, if you update your network weight using some data, and then after a while you switch to other data, the network is going to forget the old data and instead fit the new data. So it's actually quite well suited for the setting of RL, where you have to like shoot a moving target. So the issue with training a neural network is that even though you can think of it as a standard optimization problem, typically you cannot afford to solve it as a standard optimization problem because of the size of the problem. So that's not going to be actually the case for what we're going to see here in class, because we're going to work with small networks. But when you want to solve like real challenging problems in the real world, then your networks are gonna have a huge number of weights, like millions or billions. And so you cannot tackle this problem using the standard optimization method like Newton's methods. Because for Newton's method, you need to compute the Hessian and invert the Hessian. There is no way you can compute and invert a Hessian of when you have W to be like a billion. So we need to rely on optimization techniques that are cheaper than Newton's method. And so typically these are going to be different variants of gradient descent. So gradient descent, we talked about it like a month ago, and it will be basically just updating the decision variables of your problem by following the negative gradient direction. We also saw that it wasn't working very well. If you remember that we had all these convergence problems where we were jumping from one part to the other of the minimum. And so convergence was very slow. So that's why actually there are some improvements over gradient descent that we can use. Maybe you have already heard about ADAM, for instance. It's a very well-known algorithm for training neural network, which is an improvement over gradient descent. So already a little improvement that we can take is to switch from classic gradient descent to stochastic gradient descent. And here the idea is extremely simple. So in classic gradient descent, you will need to compute the gradient of the cost function, which depends on all the data set. But if you have a large data set, then evaluating the gradient of the complete cost function can be very costly in terms of computation time. And so every time you have to take a gradient step, you pay a high computational cost. So in order to lower that computational cost, what you can do is that you can compute the gradient using only a subset of the data set. So if you have a data set of, I don't know, 1 million pairs of input output, maybe you take only 1,000 pairs randomly sampled in the data set, and you compute the gradient on this subset, and you take a gradient step using this approximate gradient. But that's exactly what stochastic gradient descent does. And in the limit, actually, you can do this by sampling every time only one sample from the data set, computing the gradient only on that one sample and taking a step. The implication of this is that every gradient step is going to be incredibly cheaper than computing it on the whole data set, because, well, you're doing much less computation for the gradients. But it's going to be much more noisy because it's computed only on a subset of the data. So you can think of it as being like a noisy gradient computation. which means that it's going to take many more iterations to converge rather than a classic gradient descent approach. You have a question?
How do we select the subset?
Randomly. Typically, you just take random.
I'm not sure if I understood it correctly. You said you could go down, so your subset is only one single value, one single.
It can be even just one single value, yeah.
So I would adjust my gradient, or I'd calculate my gradient after every single value, and then I would go up or down depending on where my gradient is.
Yeah.
Okay.
Yeah.
And then I just choose that single value randomly.
Randomly, yeah.
Okay.
So that's on average, you're looking at all the data.
Yeah.
Because you have a uniform probability of sampling any data point. And so after a while you do this, on average, you're going to have seen every data point roughly an equal number of times.
Why am I like, I understand that if I do whatever, like 1,000 out of 1,000,000 values, that I choose them random, but it could also, if I'm going to adjust my delta J in this case, at every single step, and for every single value, I could just go through the whole list, couldn't I?
Yeah, but the problem is that every time you compute the gradient, you update W by a little value. Yeah. Because gradient descent is going to take small steps.
W are the weights.
W are the weights, are your decision variable of the problem. So and to converge, you will need to change W by a considerable amount.
Yes.
Because typically the optimal weights are far from the initial weights that you start with.
Yeah.
So you need to take many iterations of gradient descent to converge. If every iteration is very computationally expensive, then the overall process is going to take a long time.
Yes.
So what has been seen is that actually every gradient step does not need to have like the exact gradient to move you in the right direction. It can work well even if you have an approximate gradient.
Yes.
And so what we are doing here is that we are working with an approximate gradient by computing the gradient only on a subset of the data.
And that would be in this case only one. And I need to pick that randomly because otherwise it wouldn't be.
Yeah, I mean, in the limit, it can be only one, but in practice, that's not what people do, because if you take the gradient just based on one sample, it's going to be super noisy.
Yeah.
So what works better is to take a mini batch. So maybe like 1,000 values. You compute the gradient based on those 1,000 values. And that turns out to be very often like a decent approximation of the real gradient.
If we already say we're not taking the whole set, but only a subset, then mini batch, if I'm correct.
Yeah.
Why, if my mini batch is small enough, I could also just do the normal Newton step and then calculate the action because it's not that big anymore. Because like the reason we didn't do the Newton.
No, but the size of the action depends on W. It doesn't depend on the size of the mini batch.
Okay.
And W can be very large.
W can be large with every node.
Yeah, W can be large, but the mini batch can be small.
I see. Thank you.
So stochastic gradient descent is like the basic algorithm that you would use for training a neural network. And then you have like variations like Adam, which I was saying before. And there are many other algorithms which are kind of like Adam, which are trying to replace the fact that we don't have a Hessian when we do stochastic gradient descent by trying to learn to estimate an approximation of the Hessian online using only gradient information. Okay, I'm not going to explain you how these methods work, but just to give you an idea, you can think of them as like approximate Newton's method that are much cheaper to compute because you don't really need to evaluate the Hessian. You just use the gradients that you compute to get an estimate of what the Hessian should be. And so that introduce some term here which acts a bit as a Hessian regularization. Anyway, these methods are all already implemented in standard neural network libraries like PyTorch or TensorFlow. And so typically you don't need really to implement them. You can just use them with standard setting and they work pretty well. The only hyperparameters that you typically have to tune are, well, the mini batch size and the learning rate, which would be basically alpha. Okay, so since we have been going for 1 hour, I think it's a good time here to stop for a break. I'll see you back at 46. Okay, so we have seen that we can fit a neural network to any data that we have in the form of input-output pairs. Let's now see how we can use these function approximators inside our reinforcement learning algorithm. So what we want to do, just to make things simple at first, is to fit a network so that we can learn the value function. But contrary to the standard supervised learning setting in reinforcement learning, we don't know the value function. It's something that we have to figure out. So what are going to be the data, especially the target that we ask the network to fit? Well, actually, this is a problem that we have kind of already solved, because we know that for learning a value function, we have two options. We can either go for Monte Carlo. So every time we run an episode, at the end of the episode, we can go back to all the states that we have visited. And for each state, we compute the cost to go, starting from that state until the end of the episode with proper discounting. And that gives us the target that we want the network to fit. So one option is to use the cost to go for every state visited in the episode as a target, which would result in the following update for the weights of the network. This is just the gradient of the loss function. The loss function is a quadratic. So this is how the gradient comes out of it. In alternative, we can use temporal difference learning. So in temporal difference learning, we do bootstrapping. So the target is no longer going to be the cost to go, the complete cost to go of the episode, but it's going to be just the instantaneous cost at that state plus discount factor times the estimation of the value at the next state. And the estimation of the value, we're going to do it using the neural network. And this is just the same gradients, but where you replace the cost to go with this. So if you do Monte Carlo, you can be sure that you're going to converge at least to a local optimum, even if the network is a nonlinear function approximator, which is typically going to be the case. With temporal difference instead, the only guarantee is that in case the network is a linear approximator, you're going to converge close to the global optimum. So basically, if you're using temporal difference learning with nonlinear approximators, you have no guarantees at all. Monte Carlo gives you better theoretical properties than temporal difference, because Monte Carlo is much easier to analyze. Yes?
Phi is not phi of x and w is not a
Wait.
I thought that was the approximated value function of mine.
Yeah, I mean, phi is your neural network,
Yeah.
which takes as inputs the state and the weights, and it gives as outputs the value of that state.
And it's approximating my value.
And it's approximating my value function.
In every difference, I'm using my current approximation.
Yeah, as we were doing in the tabular setting, we are just doing the same here in the nonlinear setting with a continuous value.
Thank you.
Okay, so this is two possible ways of updating your value depending on the data that you collect during an episode. So in the previous slides, the math was for the standard state value function, but you can imagine we can do exactly the same for the action value function. It's going to be exactly the same equations. You just replace the value v with the action value q. But then if you want to turn this into a reinforcement learning algorithm, we also need to take care of the policy. And for the policy, if the action space is still discrete, then we can just do epsilon greedy as usual. Nothing changes. It's just that for computing the greedy action, we will need to evaluate our network for all possible actions and then pick the one that results in the minimum action value. And this is why actually this format for representing the action value is very practical, this one here. Because if you want to choose the greedy action using this format, you just evaluate the network once for the given state, and you get immediately all the action values for all the actions, and you can just check which of these outputs is the minimum, and that tells you which action you should choose for being greedy. So this one makes it very efficient to compute the greedy policy with respect to this one, where instead you need to evaluate the network for every action. Of course, if your action space is not discrete, you don't have such an easy life here. It's much more challenging because you will need to minimize a function which is continuous with respect to you. So that in itself is a challenging optimization problem to solve every time you want to take a greedy action. So that's a challenge we're going to discuss another time. For now, we are just extending the state space to be continuous, basically. We assume that the control space is still discrete. So actually, besides replacing the action value function from being a matrix to now being this neural network, the overall structure of the algorithm hasn't changed much. Okay, we are just changing the way in which we learn the action value, because now we can no longer simply replace the value inside this table, but we need to instead do stochastic gradient descent on the weights of the neural network. That's the main difference we have. So what do you think? This is going to work well? No, of course not. Well, in terms of theoretical guarantees, basically forget about them. As soon as you introduce nonlinear function approximators, all the math breaks down, and so nothing is guaranteed to work anymore. If your network, if your function approximator is linear with respect to the parameters W, then you can still have some guarantees in certain cases, not all of them. Like for instance, SARSA can be shown to work, or if you do Monte Carlo control, that's also can be shown to work. Q-learning not. But I mean, this column, in my opinion, is not very interesting because most of the time, if you really want to go to complex systems we care about in robotics, you need to go to nonlinear. So theory goes out the window. But apart from that, there are other issues which are more practical. First of all, poor data efficiency, because we are using every data point that we collect only once for updating the network, and then we are throwing it away. So we are not really squeezing out all the information that we can from the data that we collect. So we are being data inefficient by implementing our algorithm in this incremental way. So updating every time, just using the last transition that we have observed. And second, we have this problem we have already mentioned, that consecutive transitions are strongly correlated because the state evolves continuously in a dynamical system. And so here we go back to the IID assumption, this independently and identically distributed assumption of the data, which is violated. And this leads to poor learning performance of our network. So that was a first guess of an algorithm in continuous state spaces, but actually it's not a very good one. So in order to overcome these two issues, we need to change a bit how the algorithm is structured. Do you have an idea what we could do?
Every time I see a transition, I store the result. And then I use, instead of doing the gradient on one transition, I'm doing a bunch of transitions.
Yeah, exactly. So we are basically going back to that idea I told you of stochastic gradient descent using mini batches. We can apply that idea even here. So instead of just learning using the last transition, we can store a certain number of transitions in a buffer. And then we can randomly sample from this buffer a few transitions, and we can do a step of stochastic gradient descent on this mini batch. So clearly this helps in using the data more than once, because once the transition is in the buffer, then you can sample many times the same transition, and so you squeeze out more information from it. Why does it help also with the second issue? That's less obvious.
Because I guess if we have a mini batch of data, the individual learning updates are further away, and that's why they're more independent.
Yeah, because we are using data from different times, different episodes, maybe even. And so these data are going to be, at the very least, less correlated than if you take consecutive data points. Yeah. So if you use the data as they come, you're gonna use now the data at time 0, and then at the next step you're gonna use the state at time 1, and then the state at time 2. And so you're updating your network using data that is very much correlated, because the state at time 0, 1, and 2, they are very much correlated. They're probably going to be very close in state space. because your state doesn't jump from one place to another. It evolves continuously. And so the data are not independent. But if instead you store all the data in a buffer, and then you sample randomly from this buffer, well, you're going to take a data point that corresponds to a given time, and another data point that corresponds to a completely different time. So there is still some correlation between these data points if they are sampled from the same episode at least. But in general, this correlation is going to be much smaller because the system has had time to evolve between these 2 points. And well, if they are independent episodes, then they're actually completely uncorrelated. And so we have a much better independence between the data points that we use for updating the network. So this is basically the idea of batch learning. So learning from batches instead of in an incremental way, just using the last sample. And the buffer I was mentioning where we store the data, it's called experience replay. It has this very fancy name. So people in machine learning and reinforcement learning are very creative when they come up with new ideas, new algorithm, and they give them this fancy name. So this is called experience replay because it allows the learning agent to replay the experience it has collected in the past. I would have just called it buffer. Sometimes it's called replay buffer or experience replay buffer. You have all the different versions. So this buffer typically has a finite size. So after a while, the information that is too old is kicked out of the buffer so that it contains only the most recent data. You don't want to remember data that is too old because otherwise, well, you never forget the old data, and so you struggle fitting better the more recent data. And since we have a moving target, remember that, you need to at a certain point forget old data. So how long this buffer should be is going to be a hyperparameter of your algorithm. You have pros and cons, of course, for making it too long or too short.
So just to understand it, let's say I have my data with m data points for data sets, I don't know. And then I divide this into smaller batches, which I take to train my network. After each training with that little batch, I do the calculation of my gradient with the subset of outputs and inputs. And then I update my weights and throw away that set, and then I use a new set.
You throw away, I mean, not really. I mean, the data in the buffer remains in the buffer until you have added enough data in the buffer to kick that out.
Yeah, that was my next question. Am I using like a constant buffer and I kick out one data item and then add another, or do I have like whatever 100 items in my buffer, use them to train, then calculate, and then do my weight adjustment, or do I and then throw all of the 100 out, or do I do one by one and it's like a
so your buffer has a fixed size typically. I've never seen a buffer with a like changing size.
Yeah.
So typically you decide how big the buffer should be at the beginning.
Yeah.
And you start running episodes, and every episode you run, all the transitions, they go in the buffer. Okay. And then at a certain point, you also start sampling from the buffer for training.
Sure.
Okay. And you keep doing this. At a certain point, the buffer will be completely full. And so when you try to put in more data, what happens is that the oldest data goes out of the buffer, and the newest data enters to replace it. So in the buffer, you always have the most recent n transitions that you have experienced.
But like, do I every time, like how often do I update my weights?
That's a hyperparameter again.
Okay. Okay, I was wondering if I do like every time my buffer is completely full of a new set.
No, you do it much more often.
Or if I do it every time I add another.
You can do it, I mean, often you do it at every step,
Yeah. Okay.
or you can do it after every episode. It depends on you, basically. Everything can work.
Thank you.
But typically, yeah, either you do it every step or you do it every episode.
But then I still do that gradient with the subset with the mini batch.
Yeah, the updates are always done with mini batches now.
Okay. So I approximate the gradient. Okay.
Exactly. You don't do it on the whole buffer because that's typically too large.
Yes. Yeah.
It's a lot to digest.
Yeah.
It takes a while to wrap your mind around it. But in the end, I mean, mathematically speaking, we are not adding anything to the theory, to the math that's behind. That's why I like to go first through the tabular methods, because you don't have all these extra complications coming from neural networks and these issues of replay buffer and stochastic gradient descent. I mean, in the tabular setting, all of this stuff, we don't have it. So we can focus on the mathematical concepts. And then the mathematical concepts, when we transition to continuous spaces, they are exactly untouched. We are doing exactly the same thing. We just have to deal with these extra issues that are coming from the fact we use function approximation. But the ideas are exactly the same as before. We just have a few extra problems to overcome because function approximators are much more brittle than tables storing all the data for all the states and control. I mean, that was very straightforward to implement. Now we have to be a bit more careful in the learning side of things because we have these functional approximators that need data to be independent, identically distributed. We need to have always the same target that we try to fit. Otherwise, they struggle learning it. And so we need to add all these extra little tricks here and there to make the neural networks work well, basically. So we run episodes. For every episode, we put all the data in a replay buffer. Here, just to make things simple, I assume that we were doing Monte Carlo. So for every state, at the end of the episode, we can compute the cost to go, and that is what we store in the buffer. And then we sample a mini batch from the buffer. We apply stochastic gradient descent on that mini batch. So we compute the gradient on that mini batch. And we follow that gradient to update the weights of the network. And this eventually is going to converge to the least square solution of our problem, which is what we want.
What if I have to learn, I mean, using the Q function?
Using the Q function instead of the value function. It's the same, you just need here to add also the action in the buffer. And with this little trick of introducing the experience replay buffer, we are almost at a complete deep reinforcement learning algorithm, which is called deep Q network, which is basically a version of Q learning using neural networks. So if you take Q learning and you replace the table with a neural network representing the Q function, and you also implement a few little tricks to make this go well, you get deep Q network. Some people also call it deep Q learning because it's basically just a deep version of Q learning. And this was proposed in 2015. So it's already 10 years ago. But this was like a big achievement for deep reinforcement learning. It was one of the first deep RL methods to really show some impressive results. So the way it works, well, we are going to continuous state space, but still maintaining the control space discrete. We use a neural network to represent the action value function, an epsilon greedy policy with epsilon decreasing over time, as we have seen already. We use experience replay, and here, as you can see, the only difference with respect to the case where you learn the value function is that besides storing the state, you also need to store the control. And since it was not using Monte Carlo, but it was using temporal difference learning, you don't store the cost to go, but you store the instantaneous cost and the next state. For computing your TD target, you need these two information. And then every few steps, which in that specific paper was 4, you sample randomly from the replay buffer a mini batch of transitions of size 32, and you use stochastic gradient descent to do an update of your neural network weights. So you can see you have these hyperparameters, like how often do you update the weights? This is every 4 steps. Why not every 8 or every 2? No one knows. I mean, they probably tested a few values and they found out that 4 worked well, so that's what they used. And how big should the mini batch be? 32. Why? Who knows? It works well. Okay, so it becomes much more an art than a science at a certain point. So this is basically everything that we have already covered, but they also had to introduce a new trick to make it work better, which is fixed Q targets to stabilize the training. So this is related to the problem I mentioned at the beginning, that you have a moving target because the action value function that you're trying to learn is changing as you go, because it depends on the policy, and the policy is constantly being improved. So even the action value function is constantly being improved. So in order to make this process a bit more stable, so to make the neural network learn better, they decided to introduce these fixed Q targets, which means that when computing the TD target, instead of using the current weights of the network here, they use like an old version of the network using old value of the weights. So this W with a minus would be the old value of the weights of the network, which are only updated every once in a while to be equal to the current weights of the network, but they remain constant for a certain number of updates. And this helps in terms of stability of training, because at least the targets over which we are updating the weights remain constant for a little while. Again, how often should you update the target weights? That's a hyperparameter.
But that makes it more stable.
It makes it more stable, also a bit slower.
Yeah.
So you're slowing down convergence in exchange for learning stability.
How do you define stability?
I mean, it works basically. It's stable if it works. This is a very loose use of the term stability. It has nothing to do with the control theory stability that we have discussed before.
So it's just
basically what people in machine learning mean when they say the training is stable. They mean that the loss function is almost monotonically decreasing over training. You don't have high jumps up and down. And if you rerun the training multiple times with different random seeds, it always works. And you don't have it like 50% time working, other 50% time it diverges. That's what they mean by stable training. Is that training that works all the time and that basically you can stop at any time and you're going to get a good result. You don't need to monitor if it is improving or getting worse. Because if you have an unstable training, maybe it improves at the beginning, but then after a while, it starts getting worse and then it improves again. And you have these cycles of improvements and worsening. Which, is very much related to what's written down here. They also store the weight of the network, which results in the best performance because performance can get worse during training, showing that it's not very stable. And this is instead something that is very, very rare to observe in the tabular methods. They typically have a quite monotone improvement curves. Of course, you have a bit of oscillations even in the tabular setting because you're randomly sampling the initial state of the episodes. And if you're doing epsilon greedy, sometimes you're randomly sampling the action. So you have stochasticity. So having a bit of variations, oscillations, that's completely normal. But overall, the trend is monotonic improvement. Here instead, when you start introducing neural networks, you might have really that at a certain point it gets worse and that's it. You never go back. If you're wondering why, it's because of the neural networks.
But what couldn't we, if it gets worse, we could increase the buffer size again, and then it should get better.
Not necessarily. I mean, once you introduce the nonlinear function approximators, you have no theoretical guarantees, and there are counterexamples showing that indeed it can diverge. Like very simple counterexamples that show that even toy problems with nonlinear function approximators can diverge. The training can diverge. So in general, you cannot have any guarantee. In practice, with the proper amount of trial and error for tuning all the hyperparameters, people are able to make this work. But it can be painful. So this algorithm, DeepQ network, has been a big success on Atari video games. These are pretty old video games like Pong or Space Invaders. I don't know if you've ever seen them. And they were able to train policies that mapped directly from the pixels of the image of the game to the actions, which were typically joystick commands like move left, move right, and buttons like if you want to shoot in Space Invader, you press the button. The cost that they use for training is simply the negative change in score. So you would like the score to go up. So the negative change in score should be minimized. And what was cool is that they were able to use exactly the same algorithm with exactly the same values for the hyperparameters on all 49 games. So showing that, I mean, it's probably painful to find the hyperparameters, but once you find them, they can work on many different problems. And they were able to reach human level performance on 29 games out of 49, which is not bad. The neural network that they had to use is a convolutional neural networks. You need the convolutional part for treating images, because that's the only way you can deal with such a high dimensional input space. The network had 3 million parameters. So W is a vector size 3 millions. That's why you cannot do Newton's methods to train the network. And the input of the network, so this policy, is not simply the current image, but it's a history of the last 4 frames. So the last 4 images, so that the network basically can see how things are evolving in time, not only what's the current state. So in the network, you have 2 convolutional layers plus 1 fully connected layer, and they were using the classic ReLU activation functions.
Does it mean that human level performance?
It means it plays as well as you.
Oh, yeah.
The other one, games like that.
Okay. Says the computer EQ.
So this is the kind of performance they were able to get. Have you ever played this? Yes. I'm surprised. You can see it plays pretty well. The problem is that at the end they move very fast, so it's super hard to shoot them. Yeah. It won, so now it started another game, but I think that it's starting to get boring. So a few extra details. Instead of using the classic quadratic loss for training the network, they use this Huber loss, which is very common, which is quadratic around 0, but then it grows linearly when you're getting far from 0. So you have this like piecewise definition. And instead of using standard stochastic gradient descent, they use one of those variants I was talking about, like Adam. This is another variant called RMS prop, which tries to make the learning more efficient by introducing some like Hessian estimation. Epsilon, as usual, they started from 1, and then they make it decrease until 0.1 or 0.05 over the first million samples. Of course, this takes millions of samples for training. Is not something that is trained fast. Okay, so in conclusion, we have seen how we can introduce function approximation to scale RL algorithms to continuous action spaces or to very large discrete spaces. Sorry, not action, but state spaces. We can use then stochastic gradient descent or some of its more modern variants for training this neural network. We can do the training in an incremental way, updating the weights of the network at every step with the most recent transition. Or we can switch to instead batch learning, where we store all the transition in a buffer, and then we sample from this buffer, which helps using the data more time, so that it's more data efficient, and also breaking the temporal correlation between the data points. However, action space was still assumed to be discrete with these algorithms, And what was really cool, I think, that we have just witnessed in the DQN paper, that you can replace the state as the input for your policy with just sensory data without changing anything in the algorithm. So compared to everything we have seen so far, now the policy doesn't take as input the state, but it takes as input just this image, which is like a sensor space. Actually, it's the history of the last 4 images of the game. But we haven't changed anything in the algorithm, it just works. And this is something that people do even with robots. So if you apply these algorithms, these are algorithms on robots, you don't need basically to do state estimation. You can just give as input to the policy a sufficiently long history of sensor data. And then the algorithm figures out how to map from this sensor data to the actions, which is super cool. I mean, with optimal control, it's much harder to do that. Okay, I think we can stop here, and I'll see you back on Monday.